Hey, chemistry students, welcome as we begin talking about colligative properties here, and we're going to specifically look at the calculations involving boiling point elevation as well as freezing point depression. So some of the basic notes that we need to get down here for the calculations for these colligative properties is first starting off with the boiling point elevation. Basically, the equation that you need to write down is right here. The delta TB equals KB times M times I. And each one of these values here, you're going to need to know. Delta TB as being the change in the boiling temperature, and it's always added to the liquid's original boiling point. KB is a constant. It's the Moal boiling point constant. So very important that you have that put in, which depends on the solvent. For water, the KB is always the 0.51 degrees Celsius per mole. Little m is the molality of the solution, and remember, molality equals moles of solute divided by the kilograms of solvent. And that's very significant that you know that it's the solvent on the bottom, not the solution. And I, we're going to talk about a little later as being the Van Hoff factor, which is the number of ions produced when the substance dissolves. And again, this is going to be different for an electrolyte versus a non-electrolyte. So to get these KB values, you're going to have a table similar to this. You'll be provided with that, or again, it's in your book, and you can look up the normal boiling point for different solvents. You can look up the KB, which is that Moal boiling point constant for those different substances, as well as their freezing point that we'll talk about when we do freezing point depression. So looking at the example here of a substance that is going to be boiling, every time like water starts to boil, the bubbles can form and rise since the vapor pressure can overcome the atmospheric pressure. So it's higher and it's able to escape out into the gas stage. And some practical applications that we see of this is really antifreeze in your car's radiator. It makes use of the solution to both drop the freezing and raise the boiling point. Antifreeze is basically a solution of the ethylene glycol, C2H6O2. It's really an alcohol and water. And basically it prevents the liquid cooling system from freezing and cracking the engine block. So this is a great practical application to make sure that you know when we're talking about colligative properties. So let's go ahead and look at then freezing point depression and what that is. The solution freezing points are always lower than that of the solvent liquid. So that's important to remember. We made note of that before. We use a similar equation to calculate the freezing point here, and it's delta TF equals KF times M times I, where delta TF is the change in the freezing temperature, which is always subtracted from the liquid's original freezing point. KF, again being the Moal freezing point constant, depends on the solvent. For water, you need to know the KF is 1.86 degrees Celsius per mole. Again, molality, we talked about that as being moles of solute per kilogram of solvent. And I is the Van Hoff factor, which again, we've already mentioned as being the number of ions produced in solution. You have the same table that you would look here to find your KF and KB values. So there's your KF value, and here's your KB value. Those are constants. They're always given to you, maybe indirectly because you have to look it up on the table, but you're always going to be given a K value. So looking at some practical examples here is actually when we add salt is added to the roads to melt the ice because it reduces the freezing point of the water. A very significant example to know that because we see it so much in Ohio out on the roads in the wintertime. Another example of a frozen solution is a popsicle. And basically, if you actually think about, if you have a popsicle and you suck on it, you're going to end up with a very sweet solution that comes out of it. And basically, all you're left with is a tasteless stick of ice water on your popsicle stick. And that's a good example there of freezing solutions for us to enjoy, like ice cream. So let's kind of compare the two here, that the boiling point and the freezing point. We've said this before, but in both equations, the change in temperature, the delta T, does not depend on what the solute is, but only how many particles are dissolved in that solution. And again, for each one of these equations, we do kind of have our I value here also, kind of write that in. It does help us for solving these problems. So we talked about this I value, right? We talked about I, and what is it? And we said that it's the Van't Hoff factor. Well, we've talked about ionic solutions dissolving in water, and that when they split up, they're going to form multiple parts in water. And a good example here is your calcium chloride, CaCl2. It actually dissociates into calcium plus 2 plus a chlorine -1 and another chlorine -1. So one formula unit or molecule splits up into 3 ionic particles. So for this equation, I equals 3. And that's what we're talking about as being the Van't Hoff factor, or I. The colligative properties depend on the concentration of dissolved particles, not what kind of particles they are. So if I have more particles, I'm going to have a greater effect on my colligative properties. So in that example, 1 mole of an electrolyte can break up into 2, 3, 4, or even 5 dissolved particles. These substances have the 2, 3, or 5 times the effect on the freezing and boiling points as the non-ionizing solutes. Again, non-ionizing means not forming ions in solution. So I, in our equations, is equal to the number of ions formed from a dissolving salt. And usually all of these dissolving salts are always going to be our electrolytes, and that's why we talked about identifying electrolytes versus non-electrolytes. Looking at non-electrolytes as a form of I values, it's very significant to have this down here. I always equals 1 for non-electrolytes. So in this example here, we have C12H22O11 dissociates. So if it was put into water, it's going to say C12H22O11 aqueous. So the I value equals 1. So let's put this to use here and solve some example problems. Calculating the boiling point of a solution if we're given 5.9 grams of a sodium chloride and we're putting that in 1 gram of water. So you can kind of imagine yourself at home boiling some water to make some spaghetti, and you're going to put a little salt in because you've always heard that makes the pasta cook faster. Well, why is that? And kind of the concept here is that if you raise the boiling point of the water, that means it can get to a hotter temperature, thus cooking the pasta faster. So let's see what adding 5.9 grams of this sodium chloride actually does to the boiling point. So since we know that we are finding the boiling point of a solution, we go to our equations and we remember that the delta TB, which is boiling, is going to equal the KB, the constant boiling point for our substance, which is water. So that is going to be our KB, times M, which is the molality of the solution, times I, which is the number of ions that form out of solution. So to find each one of these here, your delta TB is actually your unknown. KB is a constant from the table, and you can always look it up, or you always be given the constant for water, which is going to be 0.52 degrees Celsius per mole. You have M, which is the molality, and remember that is moles of solute per kilogram of solvent, kg solvent, and then I, which is your number of ions. So to find the molality and the number of ions, we're going to have to do a little bit of work here. We need moles of solute, and you see that we're starting with 5.9 grams of the sodium chloride, so I need to do a mole conversion. 5.90 grams of my sodium chloride, NaCl, and we're going to do a simple gram to mole conversion of grams of NaCl to moles of NaCl. It's always 1 mole, and I need to find the molar mass of sodium chloride. So find the periodic table and add up their masses. And finding the mass of sodium chloride at 58.45, I can then simply divide my 5.9 on my calculator by the 58.45 to obtain 0.101 moles of NaCl. For the number of ions, I know that NaCl, when placed in water, H2O, will separate into Na plus and Cl negative because the charges on the periodic table, group 1 and group 17, give me their charges. And this really is going to form 2 ions. So the I equals the number 2 in this case. So now I have all of my variables that I need. I can substitute into the equation and go ahead and solve my problem. So substituting in here, we have our delta T B equals Kb, which is 0.52 degrees Celsius per mole, times M, the molality of the solution, which is moles per kilogram. So there's my moles. So I'm going to put in the 0.101 moles per kilogram of solvent. And in this case, I gave you 1 kilogram. Whoops. And make that a parentheses, not a straight line there. So 1 kilogram. And then my final I times I, which is 2, because I form 2 ions in the solution. And type this in our calculator, and we will end up with delta TB, the change in boiling point, to be 0.105 degrees Celsius. That's the change in boiling point. The problem wants to know, calculate the boiling point of a solution. Well, we know water, pure water, boils at 100 degrees Celsius. And if the boiling point is going to change by 0.105 degrees Celsius, my final boiling point is actually 100.105 degrees Celsius as my final answer. And it only goes up a very minute amount. 5.9 grams of salt is quite a bit. So the next time that you add some salt to the pot of water that you boil, it's not really going up that much in temperature. You have to add a lot of salt in order to get it to go up a high temperature. So let's look at another example here of how freezing point can affect the solutions. We're going to look at freezing point depression of water in a solution of 17.1 grams of sucrose in 200 grams of water. What's the actual freezing point of the solution? So let's start off by writing down what we are given. We're we're asked to find what's the freezing point depression of water. So freezing point depression is going to be my delta TF. That's my unknown. 17.1 grams of sucrose. That is going to be my grams of solute, because that's what's getting dissolved. 17.1 grams of the C12H22O11 in 200 grams of water. So my grams of solvent is 200 grams. What's the actual freezing point of the solution? And I know that my equation that I want to use is delta TF equals KF, the freezing constant of water, times M, which is the molality of water, times I. To find the KF value, I look at a table because it is a constant, so that I am given the KF of water at negative 1.86 degrees Celsius per mol. My molality, I need to convert here, so I will simply set up to solve for M. I'm going to set up a simple conversion to convert my grams of solute into moles. So I have grams of C12H22O11, and I'm going to 1 moles of my sucrose. I need to add up 12 carbons, 22 hydrogens, and 11 oxygens. So let's go ahead and do that on our periodic tables. Finding the molar mass of sucrose to be 342.34 grams, I can divide 17.1 by the molar mass to obtain a 0.050 moles of the sucrose. Down here for grams of solvent, I know that molality is moles per kilogram, so I need to convert my 200 grams to 0.2 kilograms. And I know we have our kilograms of solvent. I need to find my I value. And since sucrose is a non-electrolyte, the I value of all non-electrolytes is 1, since they do not dissociate or ionize in solution. Now that I have all of my variables, I can go ahead and substitute in to solve. So my delta TF is going to equal the freezing point constant of negative 1.86 degrees Celsius per mol times the molality M of the solution. So it's 0.050 moles per kilogram of solvent, which is 0.200 kilograms, and then of course times 1 for the I value. So I can substitute in and then simply type in my calculator to obtain the final answer. Finding the final answer of negative 0.465 degrees Celsius as my delta T value is the freezing point depression, so that's how much it's lowered by adding that much sucrose to water. And then the actual freezing point of the solution, since typical water freezes at 0 degrees Celsius and it's being lowered by negative 0.465 degrees Celsius, the final answer is negative 0.465 degrees Celsius as the new freezing point of my solution. So in this case, both answers are identical. The last problem that I want to look at here is a little bit of a more complex example problem where we are actually asked to find the molar mass of the solution. So what is the molar mass? So my molar mass is unknown, and I measure molar mass in grams per mole of 34.5 grams of a non-ionizing. And this is a key here to see that it's non-ionizing, which means that my I equals 1 because it does not form ions in solution. It's dissolved into 300 grams of water and produces a solution whose freezing point depression is negative 0.963 degrees Celsius. So I have grams of solute as 34.5 grams. I know that my grams of solvent is 300 grams of water, and it produces a solution whose freezing point, so excuse me, the delta T value freezing is negative 0.963 degrees Celsius. Seeing here that it is a non-ionizing solution, I know my I value equals 1, and the equation that I want to choose is delta TF equals KF times M times I. The molality I'm going to be able to solve for as being moles of solute per kilograms of solvent. So I need to convert my solute to moles. But I don't know what the solute is. I don't have a chemical formula. And this is where we have an actual equation that we can use right here, and I'll kind of enlarge it for you to see that we can use to solve for the molar mass of a compound. The molar mass equals the grams of the compound divided by the molality times the kilograms of the solvent. So in this equation, I actually have grams, I have kilograms of solvent. I do not have the molality of the solvent, however. So that's what I'm going to need to solve for here, is I need to solve for M, and then I can plug M in to my equation because I'm given everything else to solve for the molar mass. And in order to solve for M, I can use this equation because I know my KF because that is a constant, and I'm given the change in temperature, delta TF, and I is 1. So it's kind of simple to solve here. So I'm going to substitute in here. My delta TF is negative 0.963 degrees Celsius, is equivalent to my KF, so the freezing point constant of water, which we know to be negative 1.86 degrees Celsius per mole, times the molality, times I, which is just 1. I'm going to solve for the molality by dividing each side by the negative 1.86. That cancels. Divide here by negative 1.86 degrees Celsius per mole. And I can solve for my little m, molality, to be, type it in our calculator, negative 0.963 divided by negative 1.86, 0.518. And that would be moles per kilogram because that's what molality is. I can now substitute this into my equation to solve for my final unknown. So let's go ahead and switch colors here so we have something a little different to look at, and we'll solve out our problem. The molar mass of my compound is going to equal the grams, which is given here at 34.5, divided by the molality, which is 0.518, little m, which again is moles per kilogram, times the kilograms of solvent. So my grams is going to be 0.3 kilograms. So down here I have 0.3 kilograms. And I can simply multiply and divide to obtain our final answer. My final answer of 222 grams per mole as the molar mass of my unknown compound. And that is how you calculate molar mass for colligative properties.